This is the next video in the chapter on electronic structure and periodic properties. We are finally going to talk about electronic structure. We have talked all about electrons as waves, electrons as particles, electrons as standing waves, electrons as mass equations, electrons living in orbitals, and we're finally going to talk about where to put electrons in an atom. So in the previous video, we were talking about an electron's address. We said we can describe an electron's location using an address, an electron address. And that electron address contained 4 parts, 4 quantum numbers. And those quantum numbers were n, l, m sub l, and m sub s. And with those 4 pieces of information, we could specify a specific electron in a specific orbital. But the one thing we haven't talked about yet is if anybody's actually home. How do we know if an electron actually lives in that orbital? So this is going to be important to deciding whether an electron is going to bond or to react with something else, is knowing which of these electrons, which of these orbitals have electrons in them, which of them are occupied. And we decide which orbitals are occupied using the orbital filling rules. So there are several rules that we use to help us decide. So we are going to write the rules here on this page, and then we will talk about the rules more in depth on the next page, kind of like we did in the previous few videos. So the first, most important, and most simple rule for filling electrons into the orbitals is called the Aufbau Principle. Aufbau being the German word for building up. And this principle says you fill the lowest energy orbitals, by which we mean, of course, the lowest principal quantum number orbitals, fill the lowest energy orbitals first. And up until this point, we have only loosely talked about energy. We said that a lower number of n represented a lower amount of energy, but we haven't really drawn more than 3 orbitals at a time. So today we are going to change that. Take a moment and copy down this picture into your notes. I have pre-drawn it only because it would be horrendous looking if I didn't. So here are some of the first few orbitals that exist. Remember that the principal quantum number 1 only has 1 subshell, the s. Principal quantum number 2 has 2 subshells, the s subshell, which has 1 orbital, and the p subshell, which has 3 orbitals. Here is the n equals 3 principal quantum number. The third shell has 3 different subshells. The s subshell has 1, the p subshell has 3, and the d subshell has 5 orbitals. And so as we move from low to high quantum numbers, principal quantum number, we increase in energy. It's much more significant of an increase at the beginning and a bit less of a significant increase a little bit later on. And so this is called an orbital diagram. So remember that each of these orbitals is sort of like a 3-dimensional object around the nucleus. We just only draw the top bit to help us sort them by energy. And what we're going to do is we're going to start filling electrons into the orbitals by drawing lines that look like this. So it's kind of a line, but it's like a half arrow, and the half arrow at the top tells us what the spin is going to be, because remember we decided that the spin had to be different for different electrons in the same orbital. So here's the notation we're using. Each of these lines represents an orbital, which can hold up to 2 electrons. And if we draw the arrow like this, like a half arrow pointing up, this refers to a spin up electron. Now, when you draw an electron, you can draw it either as spin up or spin down. The convention is always to draw the first one pointing up, but it really doesn't matter. What does matter is that two electrons in the same orbital have opposite spins. That's the most important part. So when we start filling in electrons, we always start here. That's what the Aufbau Principle says. It says we start at the lowest energy, and the 1s is the lowest it's going to get. So this little guy will label number 1. You do not have to label these on your own picture. This is just for you following along. This is the first electron that we filled in. And now let's think about all the things we learned way back in the last chapter when we talked about what protons were and what electrons were and what an element was. Here is our friend, the periodic table. And we said that in each of the boxes for the elements on the periodic table, there was an atomic number. And that atomic number told us the number of protons that every atom of a particular element had, which is how we define the element. We also said that most of the time, these atoms are neutral. And that means they have the same number of positive and negative charges, meaning that the number of protons is equal to the number of electrons. So let's add that in here to make sure we remember that. We are remembering from last week. Oh, going off the screen. There we go. Remember that a neutral atom should have the same number of electrons as the number of protons, so that it is neutral. So we can draw the orbital diagram or the electron configuration for a neutral atom. We can just look up the number of protons and draw that number of electrons. So we're going to use something called an electron configuration, and it's going to have terms in it that look like this. We have seen things that look like these first two parts before to specify some of the quantum numbers. Remember, the first number represents the principal quantum number for the shell. And the second part, which is a letter, that refers to the secondary quantum number, or the angular momentum quantum number that tells us about the shape. This superscript is new. We haven't used that yet, but at the very end of the last video, when we gave the map of the periodic table and we talked about the number of columns, that's what this number has to do with. This superscript tells us the number of electrons that are in a particular subshell. The number of columns in a block of the table told us about how many electrons could possibly fit, whereas this number is going to tell us how many electrons are currently there. So we need to start simple, and starting simple means starting with one electron. And if we look at our periodic table, we know that something with one electron that's neutral will have one proton, and if there's one proton, we are talking about hydrogen. So hydrogen has one electron. Its orbital diagram is going to look like this. And if we write the electron configuration, we will write 1s1, because that one electron lives in the 1s orbital, and there is one electron living in it. So let's go ahead and move our way down the periodic table. So let's move to the element that has 2 protons and 2 electrons in a neutral form, and that's helium. Helium has 2 electrons, and we are forced to put an electron somewhere else, but we need a new rule to help us decide where to put it. So back we go to our orbital filling rules for number 2. And this is one that we actually saw in the last video, the Pauli Principle. But it's relevant to how we fill in this new kind of diagram, so we're going to include it in the rules here anyway. Pauli Principle says, if an orbital contains 2 electrons, or in other words, it is full, And those electrons must have opposite spins. Remember, this is referring to the m sub s value, that fourth quantum number. All right, so knowing what we know, we can determine where to put that second electron. So we said, according to the Aufbau principle, we need to pick the lowest energy orbital. So the 1s is still the lowest energy orbital, and there is still space in it. There's still space for one more electron, but when we put it in, we need to indicate that it is of the opposite spin, so it's allowed to live there. So in this case, we're going to draw half of a downward pointing arrow. So the downward pointing half arrow is going to represent a spin down electron. And again, it doesn't matter which one you put first. You can put the down one first and then the up one, but most scientists write the up facing one first, just out of habit. So the second electron that you put into an atom will always go in the 1s orbital. And so when we want to write the electron configuration, again, we write 1s because that's where both of the electrons live, but this time the superscript is a 2 because there are 2 electrons in that s subshell. All right, let's keep going. We're on a roll here. We're doing electron configurations. We did helium. So if we want to do a 3 electron neutral atom, we'll move to lithium. And let's leave some space here so it's easier to see. So lithium has 3 electrons, and so we need to find a place to put that one. And the Aufbau principle says we always fill from lowest to highest energy. This particular shell is filled, so we move to the second energy shell. And the 2s is the lowest orbital in the second shell. So we're going to put an electron there. And I've decided to put it as a spin up. And when we write the electron configuration, it always looks the same as the one before with a little bit more added. So there are still 2 electrons in the 1s orbital. So we still write 1s2. The next electron, the third one, lives in the 2s orbital. And there is only 1 electron there. So you can see that as we move to larger and larger atoms, the electron configuration is going to become a very long list of the locations of all the different electrons and where they live. Let us continue. Beryllium is the next one. Beryllium has 4 electrons. And so this is a similar choice to when we placed the second one for helium. The 4th electron should go in the lowest possible energy location, and the 2s orbital is still the lowest energy location, and it still has a spot available. So we'll put the 4th one there. So our electron configuration will say 1s2, 2s2, because there are 2 electrons in that orbital now. Let's see, moving right along, we have done number 3 lithium, number 4 beryllium. So we should do number 5 boron. Neutral boron is going to have 5 electrons. And we are looking for the lowest energy location to put it. There is still room in the second shell here in the 2p subshell. And so I can pick any one of the 2p orbitals, the px, the py, or the pz, because they are degenerate. They have the same amount of energy. Usually we just draw it in the first one, but if you're feeling spunky, you can put it in the second or third. It doesn't matter. And when we write the electron configuration, we write 1s2 because those are still there, 2s2 because those are still there, and we add a 2p1 because now we put a 1 electron in one of the 2p subshell orbitals. Continuing, carbon is the next one. Neutral carbon has 6 electrons. And here, we're going to have to stop and add another rule because we need to decide where to put the next one, and we have multiple equal energy orbitals to choose from. Let's go back to our rules and add number 3. Number 3 also has a name. named after the scientist who wrote it, and it's called Hund's rule. And this rule tells us how to decide which orbital to put an electron in when we have multiple orbitals of the same energy to choose from. So it says, if orbitals have the same energy, and remember, if they have the same energy, that means they have the same value for N and the same value for L. If they have the same energy, the rule is that we fill the orbitals singly or one at a time before doubling up. This is just like if you went and you were sharing a room with someone that you didn't know and there were multiple beds in the room, you would choose to occupy each of you in one bed before you would decide to both sleep in the same bed if you didn't know the other person. Electrons are kind of like strangers. They like to have a lot of personal space. So according to Hund's rule, when we're deciding where to put that sixth electron, we were told that it's better lower energy option to put the electrons individually into different orbitals rather than to double them up in the same orbital right away. So I can choose to put my sixth electron in the second orbital or the third orbital. It doesn't matter which one because they're the same energy. So I'm just going to pick the second one. And so now when I write my configuration, we'll have 1s2, 2s2, 2p2 for the 2 electrons there. You can imagine for the next one, which is going to be nitrogen, if we have 7 electrons, the same rule applies. We always choose to fill individually before we double up. We've got 1s2, 2s2, 2p3. And oxygen has 8. And when we place the 8th electron, this is where we finally have to double up for the first time, because our choice is to double up one of these singly occupied 2p orbitals or to jump all the way up to this much higher energy 3s. And the amount of energy that we gain by doubling up is much smaller than the amount of energy we gain by moving to this higher energy orbital. So we're finally gonna suck it up and share a bed. So our configuration is now 1s2, 2s2, 2p4. And you can continue on like that, on and on and on, filling up all the different orbitals and even the ones that we haven't drawn here in the picture. There is one more spoiler to come on how to fill electron orbitals when you reach higher electron energy shells, and we'll talk about that in the next video.